We've been learning about momentum and collisions, and we've been talking about things like pool balls, cars, relatively small items colliding into each other. On Earth, the crust is divided into tectonic plates, and those tectonic plates move around. And as they move around, they also collide with each other. So these are enormous masses colliding with each other, far larger than anything else we've talked about. With tectonic plate collisions, it's important to remember that collisions are not just things that happen very fast. Collisions can be much slower. In physical science, a collision refers to any two objects coming into contact. I know some students have been confused when we've done examples where we call it a collision, but one object is stationary and another object is moving toward it. As long as they come into contact, that is a collision. You don't have to have both objects moving. You don't have to have any object moving very fast. The tectonic plates move relatively slowly compared to a lot of the other collisions we've talked about. Now, Earth's outer shell is broken into giant moving slabs of rock called tectonic plates. The continents actually sit on top of these tectonic plates. Here we see some examples of deformations. If we stretch a rubber band, the rubber band will return to its original shape. That's what we call an elastic deformation or deformation. With a rubber band stretches, it bounces back. Any kind of spring, it stretches or compresses, and it returns to its original shape. That's an elastic deformation. When cans are crushed, they still bend, but they don't bounce back into their original shape. We see this in a lot of examples of metals that they're bendable, right? But they don't bounce back to their original shapes. Only certain types of substances will do that. So if they bend, but they don't bounce back, or they don't return to their original shape, that's what we call a plastic deformation. And lastly, if something breaks and shatters, something like here we see a clay vase that was dropped, or a ceramic vase that was dropped and it shattered, that's what we call a fracture. So it doesn't, rather than bending, the substance that the object is made of, just the parts of it break apart. That's called fracture. So what do you think? Do you think rock, if we have these tectonic plates moving around, do you think rock can deform? Can it go through elastic and plastic deformations? Or does rock just fracture? And you might be tempted to think of rock as something that just fractures. But when we think of it on a very large scale, like when we think about tectonic plates moving around, we can actually observe deformations other than fractures. We can see rock, large layers of rock that bend before they break. This is a map showing the tectonic plates and how they are moving. So, well, the major tectonic plates and how they are moving. Where you see a red border, we see plates moving toward each other. And where we see a yellow border, plates are moving apart. And so this should make sense, because if plates are moving, if one on one side it's moving toward the next plate, then often on the other side it's going to be moving away from the plate on the other side. And this isn't something that we see. This is not a pattern that we see repeated everywhere, but that's a general pattern. Sometimes, if you look just to the east of Asia, we see a plate where the plates are moving toward each other almost all around the plate. And this is possible because of the way that plates move. So let's talk about that. In location A, this is where we are in California. In location A, you have the North American plate and the Pacific plate that are bordering each other. And the Pacific plate is actually moving up north past the North American plate. So they're sliding past each other. Plates are sliding past each other. When we feel an earthquake, that is a release of stress in that movement of plates past each other. Location B is in the middle of the Atlantic Ocean. In the middle of the Atlantic Ocean, there's a big ocean trench because the plates are moving away from each other. They're spreading apart. There are other geographic features there, but the plates are moving away from each other. So the Atlantic Ocean is actually getting bigger, right? The North America and Europe and Africa are moving away from each other. Location C over in between India and the rest of Asia, the plates are actually moving toward each other. This is where the Himalayan mountains are, and those are some of the highest mountains in the world are in the Himalayas. Two plates are moving toward each other, and when they move toward each other, they push on each other, and the crust gets pushed up, making a huge mountain range. What do we see here? We see an image of the San Andreas Fault, and again, this is the boundary between the North American plate and the Pacific plate. It's not far from where we are here in Los Angeles, and that's why we feel a lot of earthquakes here. These plates are actually sliding past each other, so they're pushed together really firmly. It's not like you're gonna see a big gap there at the San Andreas Fault. They're pushed together very firmly, but the Pacific plate slides north along the North American plate, and there's a lot of friction between them. And so along that boundary, there's a lot of shear stress. So there's friction. They don't move smoothly. Stress builds up, and every once in a while, there's a little bit of movement, and that's what we experience as an earthquake. Transform boundaries are where two tectonic plates always slide sideways past each other. In your book, there's a better image of two streams with the San Andreas Fault cutting across those two streams. And you can see it more clearly there, but you can sort of see it here, where the two streams are crossing the fault, you can actually see that they're offset from each other. You can see the place where one side of the fault has moved relative to the other side of the fault, and it actually changes the flow of the streams. When two plates are moving toward each other, that's called a convergent boundary. The two plates are converging; they're moving toward each other. There is, and with this should be a term that's familiar to you: compressional stress. We've talked about compression. When two plates are pushing toward each other, you get compression, and this squeezes the rocks together and pushes up mountain ranges, and that's what we see here on the right side. Between the Indian plate and the Eurasian plate, that's where the Himalayan mountain range is, because those two plates are pushing into each other. And you can see that on the picture on the left, you can see that the Indian plate is actually sliding underneath the Eurasian plate and pushing up the Eurasian plate, creating the Himalayas. So what might happen if they continue to move toward each other for hundreds of millions of years into the future? And how will this affect the organisms that live in the mountains? Well, the mountains will continue to get taller as long as they continue to grow faster than erosion can wear them down. Over hundreds of millions of years, this could add up to hundreds of meters. They could grow hundreds of meters taller than they already are. However, the weight of the mountains is actually causing them to spread along that boundary. And that's why you see sort of a valley forming here. The mountains, the weight of the mountains is actually pushing down and causing them to spread apart. So there's a limit to how high mountains can actually get. Once you get too much weight on there, then then you're going to have the weight pushing down, even though the plates are still trying to move together. So if these mountains become much taller, that extra height would affect the climate. So it could affect the downward side of the mountains, where the air doesn't flow over the mountains quite like it does right now, and it might be drier on the downward side. The peaks might be colder. Different species might become more common, species that can survive in those cold and dry conditions. And we may even have new species evolve because of these geographical changes that take place in the mountains. At a divergent boundary, that's where plates are moving apart from each other. Now, here's another term that should sound familiar to you, because we've talked about tension. So if two plates are pulling away from each other, then there's tension at that border. Where the divergent boundaries exist on the continents, we get things called rift valleys, because the crust is stretched. You have this tension pulling the two plates apart, and think about, if you pull two things apart, they get thinner at that point where they're going to break. So the rift valley forms, and there's a picture of a rift valley on the right side, and this this crust there actually forms. There's a lot of volcanic activity here, okay, because you have a thin crust that's fractured, and the magma is actually more able to flow up through the crust. If we look at page 104, we can complete the paragraph. Tensional stress at a divergent plate boundary can form ocean basins over hundreds of millions of years. The two plates at the boundary are moving away from each other. So in the middle of the Atlantic Ocean, for example, we have a divergent boundary. Plates are moving away from each other. So the Atlantic Ocean is formed by those plates moving away from each other. So if it's an oceanic plate, if a divergent boundary is at an oceanic plate, then it can form an actual ocean basin. If it's on a continental plate, if it's on the continent, then